Okay, so let's go ahead and begin our second part in the Evidence for Evolution lecture. So in the first one, we were talking about just some examples of how we can see things, see populations change, the Galapagos finches, the moths in England, the industrial melanism. We talked a bit about artificial selection, how we humans have actually caused species to change through our direct manipulation, selecting for this trait or that trait, breeding this one to that one. All those things can cause those populations to change over time. So Darwin is the name behind all this. He's not the only one. I definitely want you guys to know that there are a lot of different scientists involved in formulating these concepts, but Darwin is the one who formulated it the best and really articulated it the best and put it out there in the public perception. But Darwin started coming up with these ideas in 1836, 1838, and then he sat on it and worked it out and studied it and researched it and did experiment after experiment after experiment for 20 years to accumulate more data to support his ideas. And he may never have gone forward if he hadn't received this letter from Alfred Russel Wallace. So we're mentioning that in the last lecture. Wallace, same concept, but he didn't consult with Darwin to develop that concept. Wallace was working here in the Indo-Pacific region, what we call Malaysia. This Wallace line is named after him. And he was studying beetles. He wasn't looking at finches. He wasn't looking at tortoises or anything like that. He was looking at beetles. And he came up with the same conclusion as Darwin, sent Darwin his ideas, and said, what do you think? So in 1858, at the Linnaean Society meeting, both Darwin and Wallace's papers on evolution by natural selection were presented. Now, evolution had been discussed, presented, and talked about for hundreds of years prior, but there was never really any good, solid support. What is the mechanism? How does it work? Etc. Darwin, and we really should give Wallace credit as well, were the first ones to be able to support it in a scientific fashion. And the critics, rightfully so, said, if this is how evolution works, show us the evidence. What is the evidence for evolution by natural selection? So the first thing we have to keep in mind when we look at evolution, it's not a straight line process. It's not A turns into B, B goes to C, C goes to D, and that's the direction. It's not a directional thing that this is trying to evolve into this. It's very random. It goes in lots of different directions, and there's a lot of chance involved. Which ones are the most adaptable? That really depends upon your environment. And the environment can change. The environment does change all the time. That's why some things are considered adaptable in one environment, yet in a completely different environment, they could be considered negative and not having a chance of survival. So the horse, the evolutionary history of the horse shows us a good example of how it is not a directional process. It's not a straight line. The ancestral horse is this Hyracotherium, and this is what we have today. It wasn't A turns to B, C, D, E, and that's the direction trying to reach this horse. It went in all sorts of directions. It was very random, and lots of these individuals, these populations, these lines of horses did well for years, but then they died out because they weren't adaptable, and the environment selected other traits. So the key again is, remember, evolution is a random process. As the environment changes, different traits become adaptable. Other traits that maybe were adaptable are no longer adaptable because they don't fit that environment. So the Linnaean Society had these papers read from Darwin and Wallace in 1858. And as we mentioned, the critics stepped up and said, well, show us a proof. Where is your evidence? And that is the key with anything that is scientifically being proven or using the process of science to support. Can you show evidence? Can you show an experiment, set up an experiment, hypothesis, run an experiment, collect data, and use evidence to support it. If you cannot, then it doesn't fall under the realm of science. So evolution is a scientific concept, scientific theory, because we have lots and lots of different lines of scientific evidence that can prove this and support it. So one line that Darwin presented that is still being used today is the fossil record. We are constantly building the fossil record. We have millions and millions of fossils in the fossil record that are continuously supporting the line or the idea, the theory of evolution. So the pattern we see with fossils, the oldest and simplest fossils are always the deepest fossils. They're the deepest in the fossil layer. The younger and more complex fossils are the superficial ones, closer to the surface. So it shows a pattern. 570 million years ago, these fossils would be simpler. They're deeper down in the rock layers or the fossil layers. And then as we move closer to the surface, we're getting younger and younger in time, closer to modern day. The fossils become more complex. They become more advanced. There's new traits, new features, and new variations showing up as they evolved and moved in this direction. So the fossil record is quite expansive in a lot of different areas. Now, one technique that's used when we're looking at fossils is this thing called relative dating. You're looking at the approximate age of a fossil due to the presence of things, let me fix the typo, due to the presence of what are called index fossils. Now, index fossils are fossils that are present only during small windows of the Earth's history. So things like trilobites and these different organisms, dinosaurs, etc., were only present in small windows of the Earth's history. So they can be used as what we call index fossils. So anything that is found in that same fossil layer, we can get an idea that it's around at the same time. It was here during the same time period as those other fossils, giving us an approximate age. So again, this is referred to as relative dating. So if you were around the same time as the dinosaurs, odds are your species is roughly the same age as the dinosaurs. If you disappear the same time the dinosaurs disappear, well, we know you disappeared about 65 million years ago, and so on. But relative dating is one way when we look at the fossil record that we can help get an idea of the age of the fossils. And again, index fossils, those are used to help identify really a period of time in the Earth's history. So in the fossil record, we find these things called missing links. These are organisms or species that are kind of intermediates between different groups of species that have existed throughout time. So an example here is called Archaeopteryx. This species shows half bird, half reptile features. So the artistic recreation is much easier to work with. We take a look at this guy. So this species had teeth. Well, that's what reptiles do. Think about alligators. They have teeth. But this species had feathers. Well, that's what birds have. They have feathers. They had claws. Okay, there's another bird feature. The tail with vertebrae. Well, now we're back to the reptiles. So this is not what we would call a reptile. This is not what we call a bird. This is an intermediate. It's a transitional fossil or transitional species. It's in between. And the descendants of this group are what evolved into birds and then into reptiles, different versions or varieties of the reptiles. So Darwin and Wallace both were looking at these types of things in the fossil record saying, here's great evidence. This continues to support the idea that species change over time and then natural selection is a driving mechanism behind evolution. Directional selection. We talked a bit about this in the last lecture. When we look at directional selection, one extreme phenotype is selected for, In the example here with the horses, there was a continuous selection for an increase in the body size of these animals. Every generation, they got bigger, they got bigger, they got bigger. So when we look at the fossil record supports this. Over the course of 60 plus million years, the body size of the horse got bigger. So we see these patterns of change over time are present in the fossil record. So it supports the idea that species have changed and evolved. So let's move away from fossils. Let's look at anatomy. Just basic anatomical evidence. Now, when we look at anatomical evidence, we have three different categories. But basic anatomy helps us support evolution and understand evolution. Okay, so the first category for anatomical evidence is what are called homologous structures. These are structures that have the same basic feature, and this is due to common ancestry. Why do you have blue eyes and your cousin has blue eyes? Because you have the same grandparents, etc. Those concepts. But now when we expand it out to the species level, look at the arm of a human, look at the arm of a cat, a bat, a porpoise, and a horse. All of us are mammals. We all share the same basic bone pattern. Humerus, radius, ulna, carpals, metacarpals, phalanges. Every one of us, same basic bone pattern. The variation between a human arm and a cat arm and a bat arm or wing is due to adaptation to their particular environment, their ecological niche, what they do in the environment. So for a whale or a porpoise to be adaptable, those phalanges, fingers, need to spread out and elongate so they can push through the water better. For humans and all primates, grasping hands. For bats, elongated, extremely elongated phalanges with skin in between to create a wing. So we look at this and say, okay, all of us have that same basic structure because we have a common ancestor. So it helps support the idea there's common ancestry and that we've changed over time. Vestigial structure is our second anatomical feature. Okay, so vestigial structures are things that have no apparent function in the species currently. But that structure was functional in our ancestor. So the example here is, look at the whale. Whales are descended from a mammal that used to walk on land. And for a lot of people, that's a big jump. But when we look at anatomically, if whales were always aquatic animals, always aquatic mammals, never had an ancestor walking on land, they would not need hips. But we see whales with hip bones. Those are known as vestigial structures. The hip bone in the whale today serves absolutely no function. But the genetics to produce those hip bones are leftover pieces of DNA from the earlier ancestor. The genes have been turned off. They don't need to use it. But occasionally whales express those genetics. So think about humans. We have features that just have no real function. What's your appendix do? Now, what do our wisdom teeth do? Nothing for us today. But if we go back 100,000 years, our ancestors used those, relied heavily on those. The appendix was a major structure used for digestion and defense with nutrients and things that we eat. The wisdom teeth would be used for grinding and crushing and tearing up food when we were eating things 100,000 years ago. But today, we don't need it. They're just not functional or not necessary in our species today, but they're still there because they were useful in our earlier ancestors. So those are two of the three anatomical features. We'll talk about the third one in our next lecture.